All right, ladies and gentlemen, I just thought maybe you were missing out on some good old fashioned Mr. Wolf PowerPoint lectures. So we're going to go over Chapter 10, the gas laws. So I created this slideshow for you. It's going to be uploaded to Canvas, and as well as this lecture. So a lot of this is going to be review from Chem 1, and I believe we may have done a little bit of it in Chem 2. But here are your basics. Okay, the one of the most challenging parts of gas laws is the fact that there are various variables for pressure. Um, we use PSI in the United States, like for your tire pressure and stuff. And but if you look inside the door of your car, it is also your tire pressure, your ideal tire pressure is also listed in kPa. That is the basic metric unit, is kilopascals. And that's the one that we're going to use probably the most often um, for gas law calculations. We could also use millimeters of mercury. If you remember the barometer that I've drawn for you, that it shows you how millimeters of mercury became a unit of pressure. That was Sir Robert Boyle that first did that. They are also known as torr. So millimeters of mercury and torr are the same units. Um, and inches of mercury is what we use on the weather in the United States. So when they tell you the pressure is 29.9 and falling, or 29.7 or 28.6, blah, 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 they're talking inches of mercury. And then, of course, there's bars, because why not? And atmospheres are another pressure unit that we use. But volume, thankfully, since we're in the metric system, we use those as liters or milliliters. N is the variable that we use for moles, and T is for temperature. Now, temperature must be in Kelvin for gas law calculations to work, because Kelvin is an absolute temperature scale based on absolute zero, whereas Celsius is a random temperature scale based on a random number for zero, which is the freezing point of water, right? And so there's the simple gas laws. There's the first gas laws that were discovered, the relationships between individual variables, and that is Boyle's law, Charles' law, Gay-Lussac's law. So what I have listed on the screen here, we have uh, Boyle's law right here, we have Charles' law right here, and then we have Dalton's law of partial pressure. So the Boyle's law is relating volume and pressure under constant temperature and amount of particles. The uh, Charles' law is relating volume and temperature, considering constant pressure and a closed system where there is no particles exchanged. And then we have Dalton's law of partial pressure, basically stating that the total pressure exerted by a mixture of gases is the contribution of the individual gases and their partial pressures. So the pressure of each gas exerting its force upon the walls of the container. This gas law should make sense to us, because gas laws exert pressure, or gases, I'm sorry, exert pressure by colliding with the walls of their container. So if you have a mixture of, like, let's say air, right? Nitrogen and oxygen primarily, the pressure, the total pressure of the air is going to be caused by the pressure of the nitrogen colliding with the walls and the oxygen colliding with the walls, right? And that's going to be relative, of course, to their individual contributions, right? So when we combine these gas laws together, we get the ideal gas law, PV equals nRT. And this is often also additionally manipulated so that you can get the density equation. So you can relate density to the molar mass of a gas. And so you can calculate, based on the density of a gas, you can calculate its molar mass, which is kind of useful in the lab, or utilizing those situations, those constants, right? If you know the molar mass, you can calculate the density that a gas is going to exert at a certain pressure and temperature. Here's a key component to calculations that we need to consider in real life. So when you are collecting a gas over water, this is often the way that we are collecting gases. You have to include the vapor pressure of the solution. So if you're collecting that over water, the solution is primarily water. And so you have to look up the vapor pressure of water for that temperature. okay, the temperature that the gas is being collected at. This is a vital correction factor, right? Because the gas that is in this flask right here is not just the gas that you are generating, it is also the water molecules that are hitching along for the ride, okay? And that's very important. It's very key. Okay, uh, there's a couple terms that we use when we're talking about gases. We're talking about diffusion versus effusion. Gases diffuse, as in they move from an area of high concentration to low concentration, because that's the way that gases work. That's the way everything works, right? You've learned this in biology. We've done this in chemistry, right? But we're differentiating now between the terms diffusion and effusion. Okay, so effusion is the exact same concept, right? Gases move from an area of high concentration to an area of low concentration. That's what they do. But in effusion, you're doing it through a small hole. So small hole, right? Uh, this is like, so when you're using an aerosol spray, right? You have a gas that is effusing through a small hole, right? Because you're and a small hole, it goes through that. Diffusion is like there's a scented candle in the room and then you smell it, right? Because the concentration of the smelly gases is going from an area of high concentration by the candle to an area of low concentration, which is at your nose, right? Kinetic molecular theory, we've talked about this. We have, right? But here now I'm telling you some truths. Okay, the assumptions of kinetic molecular theory are either mostly true or true under certain conditions. And then so most of the time, we are going to be able to assume that gases are behaving ideally. And for most practical purposes, gases behave ideally, right? But of course, obviously, they're not always going to behave ideally because we have liquids and solids, right? Liquids and solids are a real thing. So obviously, gases aren't being gases all the time, right? There's a point where they stop being gases and start being liquids, right, or solids. And so one of the assumptions of kinetic molecular theory, assumption number one, is that gases are composed of molecules that are in continuous motion, traveling in straight lines, changing direction only when they collide. This is true most of the time, as long as you're above absolute zero. So good, right? Almost like everything that you're going to do is above absolute zero, right? We're not approaching absolute zero, so don't worry about it. The molecules composing a gas are negligibly small compared to the distance between them. This is also mostly true, right? As long as you haven't compressed your gas to the point where there's the volume of the actual particles makes a difference. Okay, that's going to be an assumption that we're going to check later on. Number three, the pressure exerted by a gas on its container results from collisions of the gas particles with the walls of the container. This is absolutely true. 100%. This is what causes pressure, right? This is what gases do to exert pressure. And this is the definition of pressure, right? Number four, gas molecules exert no attractive or repulsive forces on each other. We're actually getting into detail on intermolecular forces in the next chapter, but we've talked about this, right? We've talked about the particles having attractive forces towards each other within a solution, because that's what causes salts to dissolve in water and that kind of stuff. Like the reason why sugar can be hydrated, right? And all that kind of stuff is because of intermolecular forces between molecules, right? And so this is absolutely false, right? An absolutely false assumption. However, when a gas is at a high enough temperature, then the particles have enough energy, kinetic energy, that they're not worried about the potential energy interactions of attraction between the particles, right? Plus, when they have a lot of space in between the particles, then they don't feel these attractive forces very much. Okay, so this can be an assumption that we can make about kinetic molecular theory, even though it's not true at all, right? We can make this assumption because under normal conditions, right, standard temperature, standard pressure, the gas particles are mostly far enough apart from each other and having enough kinetic energy that they don't react too much to their attractive forces that they have for each other. And then finally, Assumption number 5 listed here, the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. That is 100% true. Absolutely. That is the definition of temperature. The definition of temperature is the average kinetic energy of the particles in a sample. So, yes, this is true. So, how do we know this, right? We know this based on the Maxwell distribution. So the Maxwell distribution is a graph of the speed or temperature of the particles and the number of particles in that sample that have that particular speed or temperature, right? Because temperature is proportional to the average kinetic energy, you could use the x-axis as temperature, or you could have the x-axis as speed of the particles, right? Here I have it as speed of the particles, okay? And so note that this is a mostly normalized distribution, right? On the right-hand side, it looks like a normal distribution, right? But on the left-hand side, it doesn't. Now, think about why that is. Okay, discuss amongst yourselves. Talk about this for a moment. If you're watching this at home, talk to your parents, siblings, pets about this, okay? It's an important thing. It's really important, okay? And conceptually, it's like vitally important that you understand why this goes to 0 on the y-axis. Okay. Now, note that up at the top here, it has a mu, but over here I have a v because it's the velocity, right, of the sample, which I wrote as a v. This is the Greek letter mu. It's a lowercase mu. It looks like a u, right? Yeah, it does, doesn't it? Anyway, this is the most probable speed. The most number of particles, the highest number of particles have this speed, right? But this is your root mean squared velocity, the average, right? The average is skewed towards the right from the most probable speed because of the right-handed tail here, because this goes on to theoretically infinity, right? And so there's a small number of particles that have a very, 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 very high speed, right? Which skews this average to the right. Okay. Now, at different temperatures, you're going to see these graphs. Okay, this is why I'm showing you these graphs specifically and talking about them specifically, because guaranteed you're going to see these. Okay, this is a molecular speed distribution for nitrogen gas. So you will notice that as the temperature decreases, right, the speed of the particles decreases. Right, that makes sense because temperature is the average kinetic energy of the particles in the sample. Kinetic energy is directly proportional to speed. So as you get slower molecules, right, they have a lower temperature. But the other thing to note is that as you increase the temperature, the graphs get wider. That is because, if you think about it, you have more particles going a higher velocity, right? But as you add kinetic energy to the particles in the sample, you also have a greater distribution in the amount of particles at different temperatures. Think about this for a moment, right? All these particles are moving around. They're moving around. They're bumping into each other, right? As they're bumping into each other, the particles with higher velocity or higher kinetic energy will impart some of that kinetic energy on the particle next to them, right? And so that particle will get more kinetic energy, but it can't ever get more kinetic energy than the particle with the higher kinetic energy, right? If you think about it, kinetic energy is always moving from higher to lower, right? So you can have a bunch of particles that are super fast, right? But every one of those super fast particles that collides with another particle has to distribute some of its energy. So you get a wider distribution when you have a higher temperature. Okay? Let that sit for a second. You can pause the video. I'm going to keep going. So deviations from ideal behavior, you can obviously have deviations from ideal behavior because we have liquids and solids. So how does that happen? Well, there's two factors, right? There's two factors that can affect the deviations from ideal behavior. The fact that a gas is not mostly empty space, right? If a gas is not mostly empty space and the volume of the actual particles matters, then you have the deviations that are occurring up here. And as you go to the right on this graph, you are getting higher pressure. And as you get higher pressure, you get smaller volume because the higher pressure compresses the gas into a smaller space, right? This makes sense. As they are closer together, then they are not mostly empty space, and the volume of the particles matters, right? Because they are taking up space. Okay, so that causes deviations from the ideal uh, behavior, right? At lower pressures, gases with higher intermolecular forces. So look at carbon dioxide here. Carbon dioxide, whoa, totally not behaving ideally at all, right? And then you have methane with a bunch of particles in a bunch of atoms in the molecule, right? Then you have O2 with oxygen, which has a bunch of electrons, right? And then next you have nitrogen, which has some electrons less than oxygen, but still has electrons. And then you have hydrogen kind of still just behaving semi-ideally because it's hydrogen, smallest gas, right? And so it doesn't have it has 2 electrons, right? H2, 2 electrons. And so not a lot of interactions there, right? So we can correct our PV equals nRT equation to reflect these deviations from ideal behavior by putting in the van der Waals correction factors. Van der Waals correction factors has a correction factor for molecular attraction. That is A, the fact that molecules like each other, right? Because there's van der Waals attractions, hence the van der Waals equation, right? And then you have a correction for the volume of the actual particles, right? Because that decreases the available volume because the particles themselves actually take up volume. And so this makes sense that these correction factors are here. Don't worry about these correction factors. You're never going to have to memorize these correction factors. And this equation is given to you on the AP Chemistry cheat sheet, but it's important to know how to use it, right? So what are these correction factors for? It's important to know that A, the factor that adds to the pressure term, right, is related to the intermolecular forces, and the factor that subtracts from the available volume is the volume of the particles. That's important. Okay. All right, so we've reached the end. This is the end of the lecture portion. There are a bunch of practice problems, right, that you will be working through, and so that's really an important part of this, is just to go through the calculations, practice this, and then talk about the explanations. When you're explaining things, make sure you're explaining things on the particle level, right? Getting as small as you can, as microscopic as possible. So if you're able to talk about atoms interacting with other atoms or molecules interacting with other molecules, that is going to be the ideal explanation for a situation, right? So good luck, and I'll see you guys in the near future.